So let's come to the next talk of the session. So it's given by Tony Mastroianni, proposed standardization of chiplet models for heterogeneous integration, or of heterogeneous integrated chiplet models, as the original title of the paper is. Let me introduce Tony. Tony has more than 30 years of experience as an engineer and engineering manager in the global semiconductor industry. In recent years, he has focused significantly on advanced ASIC package design flow developments, 2.5D, 3D. He currently leads development of advanced packaging solutions for Siemens Digital Industries software. Prior to joining Siemens, he served in engineering leadership positions at Infi and eSilicon. He earned a bachelor degree in electrical engineering from Lehigh University and a master's in electrical engineering at Rutgers University. So,
okay, thank you, Peter, for the introduction. I'd like to thank Paul for all the coordination of this conference, as well as the sponsors. So today I will be presenting on behalf of the CDX Working Group. This is a proposal for a set of standardized chiplet models to be delivered by chiplet providers to their end users, system integrators. Before I start, I'd like to begin with a brief definition of a chiplet in the context of this paper. The chiplet is an ASIC die specifically designed and optimized for operation within a package in conjunction with other chiplets. This is referred to as heterogeneous integration, where multiple die or chiplets are integrated into a system in package. For the purposes of this paper, we'll focus on the heterogeneous designs implemented on silicon interposers. So the Chiplet Design Exchange, or CDX, is an open group under the OCP sub-project under ODSA. So our charter is to recommend standardized chiplet models and workflows to facilitate the chiplet ecosystem. The group is comprised of EDA vendors, chiplet providers, assemblers, and system and package integrators. ODSA also has other groups that are working on die-to-die interface protocols such as BOW, security agents, business models, and other related chiplet topics. So the CDX group is actively working on a white paper, and this presentation today is from the modeling chapter of that white paper. To ensure operability in system and package workflows, a common set of chiplet models or deliverables from chiplet vendors is necessary. Some of the key tenets we use to comprise this list of models includes a strong recommendation for machine readable models. This is so that EDA tools and workflows can use those and take advantage of those models. We will obviously want to leverage existing standards that exist and modify those as required. And where we don't have existing standards, we'll drive the development of a few new standards also as required. Although we do recommend machine readable models, there still is a need for some level of documentation in the integration guidelines. Security agents is also an important topic that is going to be necessary in the foreseeable future. There is a working group on CDX working on that. So it was not a specific area of focus in the CDX group. So enabling a chiplet ecosystem is similar to that of an SoC ecosystem. For an SoC system, you need the key enablers are the technology. These are the processing technology. You also need the intellectual property. These are the building blocks that are used to build the logic inside of the chip. You need the tools and the workflows along with the associated design kits. And then the business models are fairly well established for the SoC. For a chiplet ecosystem, it's similar enablers, but slightly different. So on technology, this is really the 2.5D and 3D stacked manufacturing and assembly processes. For IP, the chiplets themselves are are actually the IP, the building blocks that would be used in the package, as well as the additional models that we're recommending to be included with those chiplets. Another aspect of the IP are the die-to-die interface, the different protocols that are used within the package for the chiplets to communicate with each other. Then, of course, we have the workflows and the tools. This really does require both packaging and IC tools and workflows. So it is a different model, and it does require much tighter collaboration between package and the IC worlds. So the business models, with the chiplets are similar, but there are some differences in standard parts. So the providers will be selling silicon chiplets delivered as known good die, but there's also models associated with that. And so there'll be different business models and pricing mechanisms, and as well as the support. The providers will need to provide some level of support for the integrator so they can integrate those chiplets into their IP and also debug if necessary. So the table below really is the list that we've come up with, and this summarizes the chiplet models that we're recommending to comprise a complete chiplet design kit, or CDK. So we are asking chiplet vendors to provide these models to their end users. And the list, is fairly comprehensive. So in some cases, not all these models are applicable, but there are some models that are, I'll say, required but strongly recommended, and others are optional or recommended. So I will now briefly go through each of these modeling groups, but due to time, I won't be able to get into a lot of detail, but I would encourage anyone interested in reading the white paper that goes into a lot more detail. So the first model we will review is the thermal model. ECMXL is a JEDEC standard used to model a 3D description of a chip, or a chiplet in this case, the material thermal properties, as well as the physical power maps. This model is used by thermal simulators for use in system and package level type thermal analysis. Now, the resolution of the model needs to be necessarily sufficient, detailed, so you can perform an accurate enough SIP level analysis. Now, we're going to leave that to the discretion of the chiplet designer, because they know where the hot spots are. But the recommendation is to make sure they provide a model that's accurate enough so it does provide useful information. Now, chips or chiplets often have many different modes of operation. So if those modes of operations have significant different power profiles or thermal profiles, we are requesting a separate model to be delivered for each of those models, as well as test mode. So in a test mode, the power and thermal profiles may be different. So we're asking them to provide a thermal model for test modes as well. And this next sections will include the physical, mechanical, IO models, as well as electrical properties. So physical models are used to represent the device boundaries and the top level pins and geometries of the chiplets. So we are requesting for this LEF and GDS or OASIS models. Now, we're not asking the vendors to provide a complete GDS of the entire chiplet. It's really probably something they were not willing to do, but it's really not necessary. So we're just looking for the top levels, the information, the pins and the layers that they're associated with that are relative to the packaging and integration. Now, the LEF models are used by EDA tools, and the traditional LEF models that are used for ASIC tend to be more targeted for place and route. So they may not be directly applicable for use. So we may need to develop what I call a package LEF model, which is more appropriate for package assembly. We're also asking for a SPICE netlist. This would be a top level black box SPICE netlist that could be used for SIP level LVS. And then the next group are the mechanical views. So these mechanical views provide more package-centric information that would be useful for package assembly. So this would be defining pin types, whether a pin is a micro bump, a TSV. It would include dimensional tolerances, component thickness, material properties, etc. So Zephyr XML is an open source format that is used to describe mechanical, electrical, and I/O type information. So we are recommending that format, which is an open format to capture that mechanical type information. Now, Zephyr XML also supports electrical information. So this information for standard ASICs is generally provided in a data sheet type format. So in the spirit of trying to have machine executable models, the Zephyr format also allows us to capture some of this electrical information. So this may be operating range, a voltage, power, current, ESD ratings on pins, et cetera, that type of information. Now we do have a sponsor that is willing to work with us in taking this Zephyr XML and integrating that into the JEP 30 standard. So that's something that we will be looking into in the foreseeable future. So next category is modeling. So a system Verilog model, functional model, is recommended to define the functional behavior of a chiplet. These models are used to perform a system or SIP level functional simulation of the device. So Verilog AMS may be suitable for more analog type chiplets. And then System C or Verilog AMS models may also be provided, and they can be used for doing high level architectural exploration or system level analysis. So chip power, this is the next area. So chip power models or CPMs are required to support SIP level power estimates. So separate, again, separate chiplet models are requested for each of the different functional modes if the power is significantly different, as well as the test modes. Now, a .lib model is commonly used, or Liberty model is commonly used for system on chip IP, and that's used to define a simple power as well as timing type information. So we are requesting a .lib model for the chiplet. It would be a high level power estimate, as well as the I/O timing information for some of the slower speed I/O for that. And predominantly things like test and control type signals. The high speed I/O, you're going to run signal integrity analysis. So IEEE 2416 is a standard, and this is used to define parameterized abstract power models for use in system level analysis. Now, we could also provide optional Verilog or System C models, and they could also be used, and they can include thermal and or power information, again, for system level or SIP level simulations. So signal integrity analysis is really targeted for the high-speed die-to-die interfaces between the chiplets. So the IBIS or SPICE models are requested from the chiplet providers for each of the high-speed die-to-die interfaces for the transceivers. Now, the actual channel in a 2.5D device is actually routed through the interposer. So when doing a SIP level signal integrity analysis, you'll have to do the extractions on that channel and then use the IBIS models for the chiplets interfaces, and then put those together to form a SPICE level simulation to look at the signal integrity. So one thing that might be nice is a sample channel model can be provided by the chiplet vendors, although that wouldn't be for use direct, but it may be helpful in setting up their signal integrity setups for the system level application. Now, in the spirit of executable models, touchstone models can be provided to define insertion loss, return loss, and that type of information. And eye diagrams also generally are provided in paper form, but it is possible to capture those in XML. So that might be helpful just to help with some automation in some of the analysis flows. Next topic is power integrity, and this is used to perform a SPICE level power integrity analysis at the package and board level. The chiplet CPM model models the static and transit power profile of a chip or a chiplet. It includes the RLC parasitics of that device, and the power is delivered through the power and ground pins of the chiplets. So these CPM models are used by the power integrity analysis to model the entire power integrity of the power delivery network. Now, again, separate CPM models should be provided if there's significant different power profiles in the different modes. Testing is probably one of the biggest challenges in these complex heterogeneous integration designs. So the primary test, and I'm talking about production test here. So the primary test modes that we need to look at are on the die-to-die interfaces. So for testing, just the simple interconnect test can be conducted with boundary scan, and that would be a low-speed functional type of test. It's also recommended to do at-speed or high-speed testing of these interfaces if possible. And for that, you can use scan, IO-BIST, and loopback type test. Now, although chiplet components are delivered and tested by the providers as known good die, the system integrators that are delivered to the system integrators, there still is a need to test each of these chiplets after assembly. Mustafa talked about in his last paper, there may be in the assembly process, maybe something was damaged on one of the interfaces or the actual chiplet. There may be different voltage or temperature operating ranges in the system and package application that differ than the conditions that were assumed when they were building the chiplet. So as such, we do request that the ATE test patterns and the associated deliverables and scripts that were used for testing those known good die are delivered to the end users, so and they can use those to perform the detailed ATE level testing of each of the chiplets. So the integration of these chiplets, in addition to the die-to-die and the detailed chiplet testing, there may also be a need for doing some system level type tests, and that would be left up to the system integrator to do those tests, to kind of test the overall operation of the device. Now, testing these complex. Sorry. Testing of 2.5 and 3D chips does require the use of advanced DFT solutions. So it does require following all those standards, and I have a list of them summarized here. But it is a much more complicated problem in testing these types of system at the chip level. Okay, and we talked about security. So the need to ensure the source and integrity of a chiplet component will likely become a critical requirement in the foreseeable future. So again, this was not an area of focus, but there are a lot of activities in this area, and we believe it will be required shortly. And we did include it just for sake of completeness in here as an optional deliverable. But it is something that likely will be required by users once this technology becomes more available. So in addition to all the aforementioned models, there's still a need for documentation. So this would include general chiplet type documentation and integration guidelines. So similar to IP that's integrated into chips, we would look for integration guidelines to assist the integrators in integrating those chiplets into their package. Test programs also. So there would be some documentation that would assist the system, the test engineers and the AT and the DFT engineers in testing the chiplets in the context of the SIP level. Now, if there is firmware included in the chiplet, there would most likely be some documentation required for that, as well as if there's a security agent. So there still is a need for some documentation. So in summary, the benefits of heterogeneous integration are dramatically driving the demand in new markets and application. 2.5D HBM packaging technologies and the EDA tools and workflows are relatively mature and in full production today. This is really driven by the HBM marketplace. 3D packaging technologies are available today, and they're really being deployed primarily by advanced users, the Intels, the AMDs, the Qualcomms of the world. And I don't necessarily see a full chiplet ecosystem for 3D within the next 2 or 3 years to be adopted by kind of the general marketplace. So the focus really initially in putting this list together was on 2D type applications. So talking about protocols, DDR and HBM standards continue to mature, and they're scaling up in speed. The die-to-die interfaces, there are quite a few out there, but I think the list is manageable and it's getting there, and the adoption is beginning to converge. Many of these are in production today, and some of the newer standards are in development in terms of the PHYs, et cetera. So again, the initial focus we had on the CDX work group was on 2.5D interposer-based chiplets, but we will start looking at 3D and extending some of the models that may be required to support 3D. Another area of focus that we'll be looking at next are workflows, as well as a common set of assembly rules. So if we have different chiplet vendors coming from many different vendors and different technologies, ultimately they're going to have to be integrated on an interposer. So we're going to have some collaboration and cooperation between the different foundries to come up with a common set of rules. So there are some discussions that are ongoing, and that is an area that we're going to help to get some standardization on those rules. Okay, so I'd like to thank and acknowledge the CDX authors, as well as some of the other contributors that were working on the CDX white paper. And as I mentioned, the CDX group is an open working group, so I would like to invite anyone interested in participating to please reach out. Okay, thank you for your attention and open the floor to any questions you may have.
Thank you so much, Tony. It was a very interesting subject, and so the paper is open for questions.
I can ask you to repeat the question.
Sure.
So who wants the failure? Like somebody assembles the multiple chiplets.
Yes.
From different companies.
Right.
Let's say a company sells it as a product. Is that the company responsible for, let's say, customer contract and says it doesn't work?
Yeah, the assembler, ultimately, whoever's building the system and package.
Tony, maybe, sorry for interrupting.
So
can you please repeat the question, because it was hard to hear the question.
Yes, okay, yes. So the question was, if an integrator is developing a system and package, and they deliver that to their customer, and there's issues in terms of support issues, who's responsible for that? Is it the chiplet vendors, or is it the integrator? Well, in my view, I mean, it's an interesting business and legal issue and support issue. So similar to IP, that is a relationship, an SoC between the IP providers and the chip designers. So I think it's going to be a similar model for the integrators. Ultimately, they'll need to get the support, and we'll need the warranties and such from those chiplet providers. But at the end of the day, if they're selling that chip, they're going to be responsible to their end users. So that is another interesting support challenge that is going to unwind as this ecosystem builds out.
There are two questions. Thank you. There are two questions online. One is from Pascal Vivet. Many thanks, Tony, for this clear presentation. What do you see as the most challenging need to be addressed in early R&D phase? In the R&D phase.
In the R&D phase of
What is the
designing
most challenging? Mhm.
I'm not sure I understand. R&D of,
I repeat, what do you see as the most challenging to be addressed in early R&D phase?
I think he means what needs are.
what needs R&D?
Mhm.
I think test is an area, we have a lot of good test solutions that work, but figuring out how to get interoperability between different EDA vendors' tools is going to be a challenge. Again, I think the technology is there today to do 2.5D. So I don't see a lot of R&D on the technology side. It's more on the flows and the integration, where I think we need to get the tools working better together. And I think test is going to be one of the big challenges.
Mhm. Okay. The next question is from John Knechtel. Can you outline a bit more on the needs of envisioned solutions for security? But I have to say, you have just 1 minute to answer in
Yeah,
the
yeah.
question.
Well, again, this is a very important topic. This is an area that we didn't dig into detail, but things like blockchain technology for every step of the process for all the components as well as the design, that is a problem that needs to be figured out because we have to do that. So again, we've just included it on this list, and there's a lot of area focuses in a lot of different groups. But I don't really have any specific, deep knowledge in that area.
Okay. Thank you so much. Let's thank Tony again.
Okay.
Thank you.
Thank you.